Okay, well, hey, ap2 folks. Well, as you can see, I'm not there, and you're about to watch a video that I'm producing. And if you look at the date stamp on my screen, you'll see I'm producing it this morning. So here's today's lecture. We are starting section 15.4 on the electric field. So we're going to start talking about electric fields. The video you guys watched the other day that had some good animations about electric fields, so hopefully you have some picture in your mind as we go through this stuff. But before we talk about electric fields, I want to go back and talk about gravity for a little bit because there's a really nice analogy here to make. So let's go back and talk about gravity for a few moments. To remind you, we said that the force of gravity on an object was equal to mg, where we said that they had some gravitational force. This is the mass that the gravitational force is being applied to, and this is the acceleration due to gravity. So we might have as an example something up here with some little mass, a tennis ball for example, and it is going to feel a force of gravity in that direction, and down here is Earth. Okay, and there's what we're talking about. So little g here. We called little g the acceleration due to gravity, but as it turns out, there's another word for that acceleration due to gravity. We could just as easily have called this the gravitational field. So acceleration due to gravity and gravitational field conceptually are the same thing. So when we talk about the gravitational field exerting a force, little g is representative of the strength of that gravitational field. So we also learned that another equation for the force of gravity, according to Newton's universal law, was g little m big M over r squared, where little m is the mass of this object, big M is the Earth, so it's that big mass there, and r is the distance from the object to the center of the Earth. So r would be down to the center of the Earth, that distance. Okay? Now, the strength of the gravitational field is the same no matter what mass we're talking about. In other words, we said this acceleration was the same no matter what we were dropping. The force that it feels is dependent on that mass, but the actual gravitational field doesn't. And we showed that this way. We said that that equation and that equation are the same equation, so we can equate them. So you would say the force of gravity equals the force of gravity. And when we did that, we saw the little mass canceled, and that meant we received this value for big little g. Well, what this says is the strength of the gravitational field is dependent on the mass of the Earth and your distance from the mass of the Earth. In other words, the gravitational field of the Earth depends only on the Earth and where the Earth is relative to your mass. Your mass has no impact on the strength of the gravitational field. Your mass has a large impact on the force that you feel, but not on the field that you're in. Well, the electric field works the exact same way, except instead of talking about masses, we're talking about charges. So what we could say is the Coulomb force that some charge is going to feel is going to be equal to the charge that's feeling it times the electric field. So we're being completely analogous to this equation. The force that an object feels from gravity is going to be equal to the mass of that object times the gravitational field. The force some charge feels is going to be equal to the amount of that charge times the strength of the field that it's in. So the strength of the field, however, does not depend on this little test charge. So let's write Coulomb's law the other way. We learned Coulomb's law yesterday, and we said it was a constant times the product of two charges over the distance between them. By the way, when we learned Coulomb's law, we called it Q1 and Q2. I'm calling it Q0 and Q because when we talk about the electric field, we tend to talk about it in terms of the charge that's feeling the effect and then the charge that's creating the field. And for some reason, your book decides to call it 0 and call it naught and blank instead of 1 and 2. So this is what Coulomb's law looks like with our new notation. If we equate these two equations, we notice the charge feeling the effect cancels out, and the strength of the electric field is only dependent upon the charge that's creating that electric field. So the charge that's feeling the effect of some force does not affect the strength of the field that's generated. So a diagram. You might have something like this. You might have a charge here, we'll call it a positive charge. That charge is going to create the electric field. So that charge there is analogous to the Earth creating the gravitational field. That's the guy making the field. And it's a positive charge, so the electric field emanates in the direction away. So the electric field lines start flying out of this guy in every direction away. By the way, I'll cut to the chase, cut back here a second. For a negative charge, the electric field is in the opposite direction. So if a negative charge creates an electric field, the electric field is in the direction towards the charge. For a positive charge, the electric field is away. It's a good thing to remember. Alright, so we have our charge creating an electric field everywhere. Way over here we have the charge that's going to feel the effect. We'll make that a positive charge. So that positive charge is going to feel a force. This positive charge feels a force from this electric field. Those are both positive charges, and this is the complication that we didn't have to deal with gravity. Those are both positive charges, so we know the force will be repulsive, so the force will be in that direction. So we have this charge produces an electric field. The electric field is doing something to this guy. This guy is feeling a force in that direction as a result. So we have the force, I'll label it the same, the force that this guy feels is determined by the amount of this guy's charge and the strength of this field. The field is right here. The strength of this field is dependent on the thing creating the field. And we have our two equations. We have the strength of the field and the relationship between the field and the force that it creates, which is in complete analogy to what we described with gravity. There's a gravity picture. All right, same deal. Oh, this diagram, my bad, I forgot. Better late than never. That would be r, the distance between the two. All right, cool. Let's look at a couple of problems. Back to the textbook. If we look at Quick Quiz 15.3, sip of coffee. Oh, excuse me a second, I'm back. A test charge of +3 microcoulombs, that little symbol mu, that means micro, it means 10 to the -6. So a test charge of 3 times 10 to the -6 coulombs is at a point P where the electric field, due to other charges, is directed to the right and has a magnitude of 4 million newtons per coulomb. If the test charge is replaced with a charge of -3 microcoulombs, what happens to the electric field? A, the electric field has the same magnitude as before but changes direction. B, it increases in magnitude and changes direction. C, remains the same. Or D, decreases in magnitude and changes direction. Well, if we replace the charge that's feeling the force, nothing happens to the field. What this problem is asking is, if I take this charge and change it with another charge, what happens to the field? Well, if I take this away, nothing happens to the field. The field does not depend on the test charge. It only depends on what's creating it. So the answer there would be C. Okay, Quick Quiz 15.4. A circular ring of charge has a radius b and a total charge q uniformly distributed around it. The magnitude of the electric field at the center of the ring is, well, it's going to be 0, and I'll show you. It's a symmetry thing. If I have a ring of charge, so there's my ring of charge, and it's uniformly distributed, so I've got some amount of charge there and some amount of charge there, and it would be the same amount, and there's the center of my circle. That charge is going to produce an electric field that way and an electric field that way. If this and this are the same, and it would be if the ring is uniformly charged, and that distance and that distance are the same, which it would be if this was a circle, then that field and that field are in opposite directions, same magnitude, they cancel. By symmetry, we get complete cancellation at the center of the circle. Quick quiz 15.5. A free electron and a free proton are placed in an identical electric field. Which of the following statements are true? A. Each particle is acted upon by the same electric force and has the same acceleration. B. The electric force on the proton is greater in magnitude than the force on the electron, but in the opposite direction. C. The electric force on the proton is equal in magnitude to the force on the electron, but in opposite direction. D. The magnitude of the acceleration of the electron is greater than that of the proton. E. Both particles have the same acceleration. Well, the answer is going to be C and D. C, because the electric force on the proton is equal in magnitude to the force on the electron. Protons and electrons have the same charge. So the force, which is going to depend upon the charge there, is going to be the same in magnitude. The proton and electron have opposite charges, so the direction of that force will be opposite. One will be a positive and one will be a negative force. Now D, the magnitude of the acceleration is greater than that of the proton. Why is that? The acceleration is not the same because the acceleration depends on the mass. F equals ma. Well, the mass of an electron and proton are nowhere near the same, so the acceleration that results will be nowhere near the same, in direction or magnitude. So, there we go. Problem, example 15.4, electrified oil. Excuse me just a second. I'm going to have to pause and answer something. I'm going to finish this video, so I'm going to make a whole separate video, and we'll start with example 15.4, so check the link for the next video.